by Supernova Feedback.
Set up with the microphone.
Where's the batteries?
Is it working? No. So it's working. Okay, now it's okay. Okay, so Reinhard complained that we talk too much about simulations or work too much about simulations. So I take the challenge and I'll tell you about a toy model, how to get the Koenig-Schmidt relation. This is some of the people that will be on a paper that we are preparing now. So I want to start with supernova feedback. I would say that supernova feedback right after gravity is the most important mechanism in galaxy evolution, especially if you talk about galaxies below the peak of galaxy formation. And it helps you explain many, many things. This is a partial list. The peak of galaxy formation efficiency, 10 to the 12 solar mass, a magic mass. For those of you who don't remember, we predicted actually the slope from supernova feedback energetics. And I want to point you to a talk later this afternoon by Sharon Lapiner about how supernova feedback suppresses black hole growth below the critical mass and introduces the critical mass for black hole and AGN. And there are many, many other things which were mentioned today, turbulence driving, and before UDGs, gas cores, etc. So the Koenig-Schmidt relation, that's what I'm trying to explain with supernova feedback alone. No gravity. This is the original or almost original Koenig law. We all know you can write it this way. If you want, this is the new version that we have seen several times today. It's a slope of 1.4. For me, as a toy modelist, it's 1.5. This is the paper we wrote a few years ago where we looked at the local star formation rate in star-forming clouds. And once we put here what we thought is the proper freefall time in these star-forming regions, we got this very tight relation obeying this rule on small scales with 1.5 here. And the key is that the efficiency that you have to put here is a constant. And that's the real challenge. Why is it a constant? So there are two types of theories for how you get the Koenig-Schmidt relation. The local one is usually based on the distribution of densities in a turbulent cloud, which is known to be a log normal. And from this you can derive, for the local star formation rule, a constant efficiency factor in the previous formula, more or less. You have to ad hoc decide about the critical density above which stars form, which is not obvious where it's coming from. About the global star formation rate, top-down idea, people do various models of self-regulation where we put in balance between the momentum in the vertical direction in the disk against self-gravity and feedback, driving the turbulence, disk instability, and migration. The recent paper by Krumholz, it was mentioned, is doing just this. The point is that these models do not predict the Koenig-Schmidt relation, they really assume it. My goal here is to get the global Koenig-Schmidt relation via self-regulation by feedback, in particular based on a constant filling factor for supernova bubbles, which I'll explain in a second. And the great virtue of this, it's independent of the local star formation recipe and even independent of gravity. Just supernova feedback basic physics. So I'm just trying to explain a relation of this sort without going into all the details, molecular gas, this gas, that gas. This will be a secondary to my round kite tow model. So here's the idea. Here's my disk, and it's full of supernova bubbles or super bubbles. And I would identify these hot regions with suppression of star formation, and these cold gas in between as where you can make stars. And the idea is that the filling factor of these bubbles is going to approach, this is the assumption, a constant of order half as an attractor, because if you start with low star formation rate, namely low supernova rate, few bubbles, then the cold dominates and the star formation rate is boosted up and you are pushed into this attractor. If you start with a high star formation rate, you get a very big filling factor above this attractor value, and then you must suppress the star formation as a reaction because you don't have enough cold gas where you can make stars. This is the trivial idea, the self-regulation into this attractor. Now, how does this give you a Koenig-Schmidt relation? I'm going to show you in a second that if you talk about a hot bubble of a supernova remnant, the fading radius of this bubble is going to be proportional to the number density of the ISM, I'm assuming a uniform ISM in this toy model, to this power. And the fading time, the time by which the supernova reaches this phase where it fades to the ISM, is also depending on number density the same way. It also depends on the speed of sound of or turbulence of my ISM, which I'm assuming is a constant, and the energy of the supernovae. Now, I can compute the hot volume filling factor by the volume of one bubble as a function of number density and the number density of bubbles, which can be given by the fading time times the supernova rate, which is proportional to the star formation rate. This is the hot filling factor, and the idea of a self-regulation to a constant value, putting a constant here, will tell me that the supernova rate is going to be proportional to R fade to the -3, the volume times the time from here, and given these values, you get 1.48. Very suspiciously close to the 1.5 we are looking for. So that's the basic idea, except that you can deal with different kind of bubbles here and get maybe different answers. So this is also, if it's 1.5, it means that epsilon is a constant. And if you do it a proper calculation, you get a normalization to be right, to be on order of 1%, as you get from various range of observations with a big scatter. So just to remind you what one single supernova looks like, there is an adiabatic phase. This is density, this is the ISM density, this is radius, where you get a hot bubble and a cold shell. This is after some cooling time, you stop being adiabatic, you cool rapidly, and you are in a slow plow phase, where this hot medium is almost empty, and most of the material is in the cold, very dense shell. And then you have a fading procedure, where this slows down, loses momentum and energy, until its velocity outwards reaches a typical ISM dispersion velocity or temperature. And it turns out that this fading radius is around 70 parsecs for a single supernova, and depends on the number density in the way I promised you. Now, there's a key assumption here. I'm assuming that the cold gas here does not make stars. Now, it's very dense and it's cold. Why does it make stars? It doesn't make stars because of shear, because it's very inhomogeneous, the tidal forces that prevent star formation here. And in this case, I can really, you can see it here, you can see it in this real supernova. This is the layer which is very inhomogeneous, and shear is very strong. And if you compute it, you find it will help you prevent star formation. So when I want a proxy for how much mass there is in this medium that was affected by the supernova and is not going to form stars for a while, I just need to see the volume of this, the hot volume filling factor, and that's a proxy for the mass filling factor of the non-star forming bubble. Okay, so that's one assumption I'm making here. So if I want to go into more details here, this is the basic way this bubble behave. This is the self-similar set of Taylor stage. This is the number density, this is the time. This is just from dimensionless analysis you can get this. The cooling, you compute the cooling over the bubble. I'm assuming here very simple cooling function in this temperature range we're talking about. You get the cooling time and the cooling radius, and then from this you continue to another self-similar solution in the snowplow phase, which goes like time to the 2/7. And when the velocity goes to the medium velocity, you have faded to these values. And that's typically 1 or 2 million years, 70 pascal bubble, and this is the end dependence that I was talking about. This is standard textbook thing. You can find it in the textbook. What we've done here is taken the Vela simulation that you heard about. This is one of them, face-on, edge-on gas, and computed either in the whole galaxy or in macroscopic regions of size of kiloparsecs, the hot filling factor, which we were looking for. And that's the main result from these simulations obtained by Fangio. As a function of cosmic time, expansion factor, this is the hot filling factor in 25 Vela galaxies, which in the phases where they had nice disks. And as you can see, each galaxy, which is a different color here, just oscillates up and down around a value of 0.6 with a small, not a very big scatter. And all the galaxies at all times self-regulate into a constant value. That's exactly what we hypothesized. So this was very exciting to see this result from the simulation. It was toy model first and then a test in the simulation. Just to show you that it's not really important how we define the hot in the hot filling factor. This is the cumulative distribution, volume distribution function of temperature, and you see there's a plateau here. So it doesn't matter if we choose 10 to the 4, above 10 to the 4, 10 to the 5, up to 10 to the 6, we'll get roughly the same result for the hot filling factor. It's not something that is tuned for a specific temperature. Either you're hot or you're not hot. Just to show you that, I can jump slides randomly, just to show you that we obtain a nice Koenig-Schmidt relation in this simulation. This is looking at every galaxy as a whole, and this is looking at 9 subgalactic macroscopic regions. It doesn't really matter. You get a nice slope of 1.51 or 1.549 with the zero bar with the scatter in those simulations. Now, you can do the same thing in isolated galaxy simulations, just to check that this is not special to the cosmological ones. And again, the prediction was that the hot filling factor will go like the supernova ray times n to the minus 1.5. Indeed, very nice Koenig-Schmidt relation in those simulations. And if you divide this to low redshift, high redshift simulation by gas fraction, it's isolated galaxies, you see again a narrow range with a similar scatter, slightly smaller value. So I'm not swearing to this 0.6. It may depend on the strength of supernova, etc. But something of order 0.5 is valid in these simulations as well. It's nothing special to the Vela cosmological simulations. Now you can start worrying about little details. One of them is, what if the bubbles overlap? I totally ignore this, and I just took the volume of a bubble times the number density of bubbles. But you can look at the simulations and do a Monte Carlo simulation where you put bubbles at random inside a disk, and you end up with a real filling factor, including overlaps. And this is the relation between them. So we have a little fitting formula for this. Z is this quantity here, and A is just a number. And you see that for below 0.5, it's not so much. At 0.6, there is some ratio between the net filling factor and the one ignored envelope. You can apply these corrections. Now, what about more realistic case where your bubbles are super bubbles of multiple supernova in molecular clouds, in clusters? So Kartik Sarkar, another postdoc working with us, has done analytic work with me and 1D simulations. There are many cases you want to study, depending on the cooling time and the fading time of the supernova bubble, depending on the length of the burst of supernovae or stars, and the mean duration between successive supernovae. So you have 3 parameters and a lot of parameter space. Each of them is a different case with different analytic result. So we've done all of them, and what we find is that for short bursts and very long bursts, when you can separate them, one dies before the other one starts. In those 2 cases, they behave like a single supernova. They give the same Kennebec relation automatically. In the case where you have continuous energy input by the supernovae, there's yet another solution between the set of Taylor and the snowplow, which is 2/5 and 2/7. There is a solution which is 3/5. And you can do this calculation, assume a constant flux of energy in time, and you get our summary of our results is that we always get something around 1.5, even though there can be some deviation, all the way to 1 or to 2. But 1.5 is the most robust result in most cases. Let me give you some example. This is just how we reproduce the predictions for a single supernova. The green is a simulation done with a Pluto code, hydrocode, spherical simulations, very simple. Cooling time, fading time, perfect match. And if you plot the supernova rate, assuming a constant filling factor for the hot stuff, and those quantities which you derive from the simulations, and each of these is different simulation for different number density of the ISM. Look just at the lower symbols. These are the ones with the highest resolution. So you have convergence to this very nice 1.5 slope as predicted. So that's for a single supernova, very obvious. I show you some cases of cluster supernova. So here's one. This is a short burst. We predicted it would be 1.5. It is indeed remaining at 1.5. Here is the evolution of the radius of a supernova in the case of one specific cluster, and you see that we recover the different phases, including the continuous phase. And this is one case where we don't do very well. You see the prediction are somewhat different. This would be the predicted value analytically in our model. Our model is too crude. The simulation, the spherical one, does converge again to 1.5 by some miraculous coincidence. And here is the last one, more realistic, a cloud of 10 clusters of 66 supernova each. And again, you get something close to the 1.5 when you have the enough resolution. There are other complications. Not only supernova bubble, there are Stromgren bubbles of photoionized regions around all stars. You can do the calculations there as well. And when you do this analytically, you get the Stromgren radius and the time like this. Again, the filling factor like before, and you get the result, and you end up with a steeper slope. So in some regime, if the photobubbles dominate over a supernova bubble, and the ratio of the filling factor of Stromgren sphere versus supernova bubbles is going like n⁻⁻², at high n, you get the 1.5 from supernovae. At low end, you may get a steeper slope if you are ever in this regime, closer to 2. And my last topic is about supernova bubble blowout. So far, I assume that my bubbles are confined to the disk and giving you the hot filling factor, etc. But bubbles, especially if you have big, massive clouds making stars, can eventually burst out of the disk, end up with outflows, either hot from the inside or cold and a little slower from the shell when it hits the radio. And one should take this into account. Now, it can cause recycling and cosmological inflow. If this outflow is not a strong effect, you can just assume the bubbles have a fixed size, which is the height of the disk, and derive from the gravitational balance in this disk connecting the H to the number density. You end up with something between 1.5 to 2 in the slope of the kinetic Schmidt relation when you do that. If the bubbles are much stronger, then you may think about totally different self-regulation by outflows and inflow, not by the hot filling factor. Just to illustrate how important they could be, this is a small, relatively small galaxy from Vela, and you see low number density, hot, outgoing, very fast outflows. So they can be very strong. And if you get a filling, a mass loading factor of 1 or a few, it may be, if this is typical, the outflow time scale to lose the gas from here is going to be 100 million years or more. Now, I tell you the fading time is only a few million years. So, as long as this is bigger than this, indeed the outflows are not the dominant thing in the equilibrium configuration. But you have to worry about this, especially if you have very massive clouds. Outflows may dominate, and you may have to worry about a different self-regulation, not by the confinement to hot bubbles. So this is just to show you a movie, because we do simulations also, and just to show you a small galaxy, how important a bubble can be. So some limits you have to worry about those outflows. And last point, not my work. The idea that feedback self-regulates the disk and the star formation, independent of the way you put the stars in, was very nicely done by Phil Hopkins in a few papers. And the one thing that you can see here, okay, is that you assume a star formation recipe like this, but you vary epsilon or x or the threshold. And in all cases, you converge to the same star formation rate. This is for high redshift galaxies, low redshift galaxies. Or you can change the whole recipe in very different ways, and you always converge. Now, I don't know if it's right or wrong. We are doing the same thing now with isolated galaxies to test this, and the hot filling factor as the mechanism to do this. This doesn't tell you what the mechanism is. The supernova bubbles study is, and the hot filling factor is the new thing that we are suggesting to explain something like this. So I want to summarize. How did I get there? I do want to show the summary. What happened here? Anyway. Okay. So the global Koenig-Schmidt relation in this very simplistic, crude form results naturally from self-regulation by feedback by the bubble fictive filling factor self-regulating itself to a constant value. The details of local star formation or even gravity doesn't come in explicitly. It's only based on the physics of supernova bubbles with all these complications. Remember, I never deviated from a uniform medium, which is wrong, but all this to be done. For supernovae, you typically get a slope of 1.5. It may change depending on the clustering of supernovae. Photoionized bubble a little steeper, and massive clusters may be dominated by blowouts, and you have to worry about a different version of the self-regulation. Is this too simple to be true? Probably, but you may reverse the argument and say it's so simple, it must be true. Thank you.
While Vadim set up, we have time for one quick question. David?
Well, it does something. As you heard from Hannah's talk today, it's not only supernova feedback that drives turbulence, also gravity and accretion. So you have to, in each problem, you have to worry about other effects. I was really focusing on this specific application and very beautiful, simplistic argument why it gave you 1.5 very robustly. But you have to worry about all these details as you proceed to make it realistic. I have a question to the audience. Somebody here, when I showed Phil Hopkins' results, said it's wrong. Mm-hmm. Who said it and why?
Well, it depends on your level. If you only care about a factor of 2 or 3, it's true. But we should do better than that.
What is wrong exactly?
Factor of 2.
It's true within a factor of 3. So if the star formation rate is right, plus or minus factor of 3, yes, every self-regulation will give you the same answer. But if you care about factors of 3, then there's subtleties.
Okay. What we will try to see is to check the same thing, but looking at the volume filling factor of the bubbles, identify the bubbles themselves in the simulation, see if this story is true at all. It may be totally wrong, I don't know. But it's a nice story.